Hello everyone and welcome to the fourth chapter, the Fourier Transform. In this chapter we will see that extending a real-valued function on R to a holomorphic function in a horizontal strip allows us to use the tools of complex analysis like residue theory to demonstrate capital results in Fourier analysis. So first recall that if you have f, a real-valued function on R, the Fourier transform of f is defined by the integral from minus infinity to plus infinity of f of x times e to the power minus 2 pi x psi. So the Fourier transform is complex valued dx. Of course, psi belongs to R. Now this integral is well defined if f satisfies appropriate regularity and decay conditions. For example, f must be an L1 function, or f is a smooth function with moderate decrease. So f belongs to the Schwarz space defined here. Okay. Now the power of the Schwarz space over L1 is that the Fourier transform may disturb the regularity of the function. So if you have a function in L1R, its Fourier transform may not be in L1R. Okay, but if f belongs to SR, then the Fourier transform, of course, belongs to SR. That's an important remark or an important fact in Fourier analysis. Now, the class F, for each A positive, we denote by FA the class of all functions satisfying the following two conditions. F must be holomorphic in the horizontal strip SA, which is the set of complex numbers with imaginary part between A and minus A. So, for example, this is the horizontal strip SA. The second condition is that there exists a positive constant, so that modulus of fx plus iy less than or equal to a over 1 plus x squared for all x and r, and y belongs to minus a. In other words, f belongs to fa if and only if f is holomorphic in SA, and f has moderate decrease on each horizontal line mz equal to y, uniformly of course for y belongs to minus a. For example, this function belongs to fa for all a positive. Finally, f belongs to f if f belongs to the class capital F if f belongs to capital Fa for some a positive. Now we will study the action of the Fourier transform on the class F, on the functions in class F. Now, if f belongs to Fa for some a positive, then the modulus of f hat psi less than or equal to what? To some positive constant b multiplied by e to the power minus 2 pi b absolute psi for all b between 0 and a. In fact, for b, the result is trivial for b equal to 0. So we will assume in the proof that b is strictly greater than 0 and strictly less than a. Now, also assume that for the first part of the proof that psi is positive, consider the following function g of z equal f of z e to the power minus 2 pi I z psi. And consider the following contour here with this orientation. Plus r 0 minus b okay. Now the integral of over this rectangle of g of z bz is equal by Cauchy's theorem to 0. On other hand, is equal to what? Equal to the integral over say this S1 segment 1 vertical segment 1, and this call it S2 the vertical segment S2. So the integral over S1 plus the integral over S2 plus the integral from minus R to R plus the integral over minus R to R shifted down, so by B, so call this S3 for example, or H3. H3, this is a horizontal line, we call it H3. Okay, over H3. Now the integral over the modulus of the integral over S1 of G of Z. After parameterizing, we find that it is less than or equal to the integral from 0 to b of modulus of f of minus Ri minus R minus it e to the power minus 2 pi I minus R minus it xi dt. Now, using the fact that f belongs to fa here, we can benefit from the second condition. There exists a positive constant a and so on, and we bound as follows: less than or equal to a over r squared plus 1 integral from 0 to b of e to the power minus 2 pi t xi dt. This integral here is a definite integral less than a constant, so this term here on the right tends to 0 as r goes to infinity. Similarly, we can show that the integral over S2 of the function g converges to 0 as r goes to infinity, and finally we end up by the following result. So here, let r goes to infinity, this integral vanishes, this integral vanishes, this integral becomes the integral from minus infinity to plus infinity of the function g of x. So this is the Fourier transform f hat psi. Taking this integral to the right hand side, we find that f hat psi is equal to what? Equal to the integral from minus infinity to plus infinity of the integral of f of x minus ib of e to the power minus 2 pi I x minus ib psi dx. This implies, of course, that the modulus of f hat psi less than or equal, using again that the fact that f belongs to the capital class fa, less than or equal a integral from minus infinity to plus infinity of e to the power minus 2 pi b psi. This term here is independent of x. We can pull it outside the integral over 1 plus x squared, and finally we can write psi. We can write instead of psi absolute psi, since psi, assume that psi is positive. Finally, this is less than or equal to the to b for some positive constant b depending on a and on the value of the integral of 1 over x squared plus 1 e to the power minus 2 pi b absolute psi. This is done for psi positive. Now, if we assume that psi negative, we do the same proof but using the following contour, the opposite contour of the one used in the first part of the proof, when assuming that psi is positive. So here R, here B, R plus IB, minus R plus IB, minus R, 0. Take this orientation, of course, and proceed as we proceed before. Okay, now the next theorem, Fourier inversion. If f belongs to capital F, class capital F, then the Fourier inversion holds, namely f of x equals to the integral from minus infinity to plus infinity of f hat psi e to the power 2 pi I x xi d psi for all x belongs to R. So proof. Now we are going to prove the Fourier inversion formula. Suppose that f belongs to f, or this is the main assumption, then f belongs to fa for some a positive. Now lemma, which I'll not prove, you can prove it very easy. The integral from 0 to infinity of e to the power minus a plus ib psi d psi is equal to 1 over a plus ib, where a is positive and b and r. Whenever a is positive and b and r. Now assume that b belongs between 0 and a. And let x belongs to r. Then write the integral from minus infinity to plus infinity of f hat psi e to the power 2 pi I x xi d xi, split the integral, write it from minus infinity to 0, okay, plus from 0 till plus infinity, and call this integral I2 and this integral I1. Now we can argue, we can assume that psi is no, for I2 psi is definitely positive. So using the same argument we used in the previous theorem, we found that f hat psi can be written as integral from minus infinity to plus infinity of f of some variable, let's say u minus ib e to the power minus 2 pi I u minus ib xi du. Now this implies that the integral I2, that's right, I2 equals to the integral from 0 to plus infinity of the integral from minus infinity to plus infinity of f of u minus ib e to the power minus 2 pi I u minus ib xi e to the power 2 pi I x 2 pi I x xi. Okay, so this is, I write as follows, plus here du d xi now okay, I2 equals to the integral from minus, interchanging the integrals, this can be written as integral from minus infinity to plus infinity of f of u minus ib, integral from 0 to infinity of e to the power minus 2 pi I u minus ib minus x xi d xi du. Now this term here, call it star, can be written as follows: e equal minus 2 pi minus into 2 pi plus I 2 pi u minus x into xi. So this is a here is positive since b is positive. Okay, now this is ib, b and r. So the integral from 0 to infinity over star using the lemma we introduced in the first part of the proof, or in the first part of the proof. This is equal to 1 over a plus ib. 1 over a, which is 2 pi b, plus I b, 2 pi into u minus x. Now turning back to the integral, to the main integral I2, we find that I2 is equal to what? Equal to integral from minus infinity to plus infinity of f of u minus ib du over 2 pi b plus 2 pi I u minus x. You can pull 2 pi I outside the integral and find that I2 is equal to 1 over 2 pi I integral from minus infinity to plus infinity of f of u minus ib du over u minus ib minus x. This can be written as 1 over 2 pi I integral over L1 of f of rho over rho minus x d rho, where L1 is the real line, L1 is R shifted down by B, Okay. Similarly, when xi is negative, for the second integral, or the first integral I1, we find that 1 over I1 can be written as 1 over 2 pi I integral over L2 minus 1 over 2 pi I integral over L2 of f of rho over rho minus x d rho, where L2 is the is the real line shifted up by B. Okay, now the integral from minus infinity to plus infinity of f hat psi e to the power 2 pi I x psi d psi is equal to the to I1 plus I2, and I1 plus I2 is equal to what? Okay. So I1 plus I2 equals to the integral over L1 of the function capital F of rho d rho plus over L2, okay, minus 1 over 2 pi I. Here 1 2 pi I. Suppose that f capital of rho is equal to what? F of rho over rho minus x. Now consider the contour. So consider this rectangle. Here minus r plus r minus b containing x, the fixed point in r, plus r plus ib, here minus r plus ib, with this orientation, of course. Okay, now we can easily show that the integral of capital F rho over these two segments, vertical segments, this one and this one, is or converges to 0 tends to 0 as r tends to infinity. And using residue formula, f of rho has a residue, a pole of order 1 at x with residue equal to f of x, small f of x. So using residue formula, we find that I1 plus I2 is equal to what? We find that 1 over 2 pi I of this integral here, I'll call it star. This integral here, I'll call it double star, is equal to 2 pi I f of x. And we conclude that f of x equals to what? To integral from minus infinity to plus infinity of f hat psi of e to the power 2 pi I x psi d psi for all x belongs to R.